Good evening everyone, I am Shivani Dhok and I welcome you all for the week 8 tutorial for the course of Modern Digital Communication Techniques. And again this is week 8 and hope you like this session. So like every week this session will be divided in two parts. The first part will be recap of week 8 content followed by some questions which are related to the content that was covered in week 8. So let's start with a recap of this week's content. So this week started with understanding the concept of minimum shift keying. It was said that this minimum shift keying is a special form of binary QPSK, that is continuous phase frequency shift keying, with h equal to 1 by 2, and the phase component phi t comma I is given as theta n plus pi by 2 I n. I'm sorry, I missed something here. In gt minus nt by t, and this theta n is given by pi by 2 summation k running from minus infinity to infinity ik. There should be a gt here, g of this, yeah. And this theta n is the accumulation term which is given by this factor here. Okay. Now the bandpass signal is given by the formula a cos 2 pi fi t plus theta n plus pi n by 2 minus 1 to the power I minus 1, where f1 is given as fc minus 1 by 4t and f2 is given as fc plus 1 by 4t, and the frequency deviation that we have is given as f2 minus f1, which comes out to be 1 by 2t, and I made a mistake. This is fine. This is just t minus nt by t. And yeah, this was the basic of minimum shift keying, which is, again I'll mention that it is a special form of QPSK with a modulation index as half. After looking at minimum shift keying, the next concept that was looked at was the quadrature QPSK, that is quadrature phase shift keying, and offset QPSK. So it was observed that if we have a QPSK, the maximum phase deviation that we observe uh, between two symbols or two waveforms is 180 degrees. However, if we add an offset of one symbol duration between the in phase and quadrature components, then the maximum frequency deviation observed is 90 degrees. So we'll see how exactly these two waveforms differ by taking an example in the question answer section. That will be much more clear. After looking at these modulation techniques, we went on to look at some of the spectral characteristics, and for that we again considered a bandpass signal ST, which is again real part of Vt into e power j 2 pi fct, and this phi ss of tau, that is the correlation coefficient of this signal, is given related to the correlation function of this Vt by this formula. And again the frequency domain representation of this autocorrelation, which is again the power spectral density, is related to the power spectral density of this Vt through this formula. Okay, and this phi Vv t comma t plus tau is periodic with period t. And then we found an average, a time average of this phi Vv of tau by making this as WSS, and it was found to be 1 by t summation m running from minus infinity to infinity phi IIM phi GG t tau minus mt. Okay, where this part, okay, so this is what we are having here, and this phi GG of tau is basically this function, and the PST of this, the like the Fourier transform of this quantity here gives the PSD, that is the power spectral density, which comes out to be 1 by t magnitude gf square, that is this thing gf square is basically the Fourier transform of this quantity phi phi I of f, and this phi I of f is basically the Fourier series representation of this quantity phi m, which is correlation coefficient of the sequence in, which comes out to be phi m e power minus j 2 pi fmt summed over m equal to minus infinity to infinity. Another thing that you should note here is this Vt. We are considering a special form of this Vt, where this Vt is basically summation n running from minus infinity to infinity in gt minus nt. This is gt is the pulse shaping waveform. So we are looking at the spectral characteristics of a particular type of signal, which is basically the information carrying signal. So this is the information sequence that we are having. This can take value in some particular constellation, finite constellation, and it is a sequence, information sequence, and this is the entire information signal that is being transmitted. And we are looking at this PSD, the power spectral densities, the spectral characteristics of these signals. After looking that, we went ahead and we started to look at optimum receiver design. In that, we didn't go ahead for looking at the receiver designing process. However, we started by considering an ideal channel, that is the channel gain as 1, but having an additive white Gaussian noise. That is something like this. If I'm transmitting SMT, this is what I'm transmitting. So this noise NT gets added, and what we receive is RT, where this is the same RT as mentioned here. So this is what we get in considering additive white Gaussian noise. So this additive white Gaussian noise basically has a power spectral density as n0 by 2 for all f, and its autocorrelation function phi nn of tau is basically n0 by 2 delta tau, which means that the consecutive or any time any samples of this noise process taken at any two different time instants are completely uncorrelated. This is what this quantity means. To visualize it properly, let's say this is some noise that I am receiving. Then if I take this point, and if I take any point close to it, maybe this point as well, since these two are independent, since these two are different points, both of these are uncorrelated. And since it is a Gaussian process, uncorrelatedness will imply independence. So this is what this AWGN, additive white Gaussian noise, convey to us. And this receiver structure is divided into two parts. So basically, if we have a receiver, this receiver structure is divided into two components, something like this. So the first part, does signal demodulation. And what does the signal demodulation block produce? This produces the vector R bar, which is this. And the next block is the detection or the detector. And this detector basically detects which waveform was transmitted. So what is this R vector? This R vector is basically the projection over the n basis vectors that we have used in order to generate this SM. All of these details will be discussed in a much greater depth in coming weeks. So I won't be going in much greater depth right now. So this was all that was covered in this week. If you have any doubts, feel free to ask at this point. Otherwise, we'll go ahead and look at some questions which I have planned to cover today. Okay, if there are no questions, then let me start with the questions that I had planned to cover today. Yeah, so let us look at the very first question. So what it says is, draw the waveform for in-phase and quadrature components for the QPSK bit stream. It is 1 0 1 0 and so on. So for this, let us consider that we are going for BPS, like this 1 is mapped to 1 and 0 for something like that. Just a minute. Okay. So let us say that this 1 gets mapped to plus v and plus 1, and this 0 gets mapped to minus 1. So if we have this bit stream, which is given as this quantity 1011 00010111, and if we just use this BPFSK, I'm sorry, yeah, BPSK, if you go for BPSK, then this stream will look something like this. We have this 1, then it is 0, then it will be 1 for 2 time duration, then it will be 0 0 0, then it will be 1, 0, or let's do it in this form. What we'll do is, when we go for QPSK, what we do is we divide this odd and even components and assign it to in-phase and quadrature components. So what we'll do is, this will be these things, the alternates will be basically my in-phase components and quadrature phase components. So let me draw the in-phase component with green color and quadrature with pink color. So yeah, so the first one will be the in-phase, then the second one will be quadrature component, then we have it this one, I'm sorry, yeah, then it will be 1, it will be something like this. Just to demarcate the in-phase and quadrature components, nothing else. Yeah, okay, so let us draw the in-phase component first. So this is for QPSK, this is just for QPSK and not for offset QPSK. So what we do is, for in-phase, the the first bit is transmitted for 2 time slots, 2 time durations, 2 symbol durations, or 2 bit durations to be very precise. So what we do is we transmit this first one for 2 symbol durations like this. Then the next thing is 0. However, it is the second component, so that will go in quadrature, but again it will consume 2 symbol durations of the first thing itself, like first 2 durations itself. After that, the third thing that we are having here is this 0, and that thing will contribute as in phase, which will be something like this for 2 durations. After that, we have a 1, and this one corresponds to quadrature component, so it will go somewhere here. After that, after this particular one, we have another one. However, this one will go in the in phase component. like this. Then we have this 0. However, this will go to the quadrature component. Now, after this 0, we have a 0 here, but this 0 will contribute in the in-phase component. So we have it something like this. And after that, again we have a 0. However, that will go in my quadrature component. So it will go here. Yeah. After that we have this one, and this one is an in-phase component. This is an in-phase component. Again, it will consume 2 symbol durations. After this one, we have this 0, and this will consume 2 symbol durations for quadrature component, something like this. Then we have a 1, which is again in-phase component, so this will remain here. And then we have this 1 here, that is in quadrature component, so this will go up for +1, and then we have a 0. Okay, so these are the waveforms that we have for the in-phase and quadrature component. I think I made some mistake. Yeah, there is a small mistake here. So yeah, this was 1. Yeah, so this was 1 1 0. Sorry, there was a mistake. So this was 1, and then it was a 0. Yeah, I have to delete this also. Let me have a stroke eraser. This also. Yeah. So okay, so we were at this point. And we had drawn this particular 1 in the quadrature component. After that, we have 1 here, and this 1 corresponds to the in-phase component. So this will be something like this. However, now this 0, the last 0 that we are having, this corresponds to my quadrature component. So this will attain 2 time slots, something like this. So these are the waveforms for in-phase and quadrature phase components for QPSK. These are for QPSK and not for offset QPSK. These are just for QPSK. Any questions? Okay, if there are no questions, then let us go for the second question for today. And the second question says that we need to draw the waveform for in-phase and quadrature components for the offset QPSK and for the same bit stream. Now again, I have made a small mistake here. Should be 1 0. So same thing we need to do. So again, what I'll do, similar to the previous question, I'll demarcate the in-phase components with green and quadrature components with pink, just to be clear. And I'll use a different size of marker. Yeah. So the first one is in-phase component. Then we have a quadrature component as 0. Then we have 0. Then 1, 1, 0, 0, 0, 1, 0, 1, 1, again 1, and then we have the last 0. Okay, so this is what we are having. Now for offset QPSK, what do we do is, instead of starting from 0th instant for in-phase component, we start from -1. That is, let me extend this here. Let's say this is -1, this was 0, and this is 1. So the first in-phase component will be something like this. Or in other words, the first in-phase component, the first one, will just use the only one time slot instead of consuming 2. This is equivalent to adding an offset of +1. That is, we are shifting the QPSK in-phase components to left by 1 unit. That's what we are adding an offset. Okay, so this is the first in-phase component, which was this 1. After that we have a 0, and that is a quadrature component, so that will go here. Then we have an in-phase component which is 0, and that's why this will go something like this, but now it will use 2 time slots. Okay, so this was the second thing. Then we have this 1 for quadrature component, so we have a 1 for quadrature component. After that we have a 1 for in-phase component. Okay, after this 1 we have a 0, but now this is for quadrature component, so this will go down and use 2 time slots. So this was this 0 which came here. Then we have this 0 for in-phase component, so this will be here and attain 2 time slots. After this 0 we have this 0 here, which corresponds to quadrature component, so we'll have this 0 here. Then after the 0 we have a 1 which corresponds to the in-phase component, which will go here. Then this was the one that we have considered. Now again we have a 0 which corresponds to the quadrature component, so we have a 0 here. After that, after the 0 we have a 1, and this 1 corresponds to in-phase component, so again it will use 2 times for duration. Then we have a 1 here, but now this 1 will correspond to quadrature component. Like this. Then we have a 1. Now this one corresponds to in-phase component, so it will go here. Now at the end we have a 0 which corresponds to quadrature component, so again we'll go back here. So these are the waveforms. Just a minute. So these are the waveforms that we have considered or constructed for offset QPSK. Now if you observe these two waveforms, this one and this one, The only difference that you can see is in this in-phase waveform. If you observe this in-phase waveform and compare it with this one, we can clearly see that this waveform is basically a shifted version of this. Like if I shift this entire waveform leftwards by 1 unit, I'll get exactly this waveform. Now by doing so, what we are getting is we are basically getting a waveform. We are basically when we choose a waveform, that will just change by 1 bit. Like basically here we are having 0, here we are having 1 0, then we are having a 0 0. So if you observe in this 2 time slot duration, only 1 bit is changing. However, if we look at this waveform here, it was 1 0 here, 1 0 here, same, and then suddenly we are having a 0 1, which means there is a change of 2 bits. 2 bits, and this 2 bit change will correspond to 180-degree phase shift. However, if we consider these kind of waveforms, under any circumstances there will be at most flip of 1 bit, and this change in 1 bit will correspond to only 90-degree phase shift, maximum phase shift of 90 degrees, and therefore this is giving me a better phase continuity in compared to the waveform that we are having for QPSK, and that's why this offset QPSK is many times preferred. Any questions? Okay, if there are no questions, then let's go ahead and look at the third question that I had planned to cover today. So what is it given? It is given that NT is a WSS, that is wide sense stationary process, with autocorrelation function R tau, which is 5 delta tau, where this delta is a unit impulse. So I'll explicitly mention this delta tau is unit impulse. And what we need to do is we need to find its power spectral density. So what is the relation between power spectral density and autocorrelation function? So this autocorrelation function and power spectral density form a Fourier transform pair, that is R tau, which is the power autocorrelation function. If I take its Fourier transform, then I'll get S of tau, which is equal to PST. Okay, and this R of tau is autocorrelation function. So therefore, if I need to find the power spectral density or the PST of this particular NT process, what I need to do is I just need to take the Fourier transform of this autocorrelation function that is given. So what we are having is this S tau, let me use another color, this S tau, which is equal to PST, is basically Fourier transform of this R tau, and this is nothing but integral minus infinity to infinity R tau e power minus j 2 pi f tau d tau. Let me substitute it. So this is minus infinity to infinity integral over minus infinity to infinity. R tau is 5 delta tau e power minus j 2 pi f tau d tau. Now we know this property of impulse, that if I have f tau and an impulse delta tau, this is equal to f of 0 delta tau. So this impulse basically, if it is multiplied with any function, so that impulse will attain a value or attain an area which corresponds to the value of that function at that particular location where that impulse is located. And if that is the case, then what do we have is this thing, this thing is equal to integral minus infinity to infinity 5 delta tau e power minus j 2 pi f0 d tau. So this thing is equal to 1, which is a constant, and I can take it outside. So this is 5 integral minus infinity to infinity. So f, I'm sorry, this is not s tau. Just a small mistake. This is not s tau, this is sf. Yeah. So integral minus infinity to infinity delta tau d tau, which is equal to 5 into 1 into 5. This is because we know that area under the impulse is 1. So the power spectral density for this particular signal comes out, for particular WSS process comes out to be 5. Any questions? Please feel free to ask questions at any point of time. Okay, if there are no questions, then let's go ahead and look at the next question that I have planned. So what does it say? It says that the autocorrelation function of a WSS process xt is as shown below. So this is the autocorrelation function of this WSS process xt, and we need to find the average power of xt. So here you should note that average power of xt is basically equal to integral minus infinity to infinity the PST of this yeah. So this is phi xx of f df. Okay, so this is the average power. So this is the average power of this process xt, where this thing is basically PST of xt, which is basically equal to Fourier transform of Rxx of tau. Right. So now if Rxx of tau and this phi xx of f are Fourier transform pair, then I can write this Rxx of tau as integral minus infinity to infinity phi xx of f into e power j 2 pi f tau d tau. Df. Now suppose, now look at this special case where my tau is equal to 0. So if this is the case, then this comes out to be minus infinity to infinity phi xx of f e power j 2 pi f0, which is equal to e power 0, which is 1 df. And let me name this as P average. So if we compare this equation here and this equation here, so these are exactly the same two quantities. So this is equal to P average, and this P average is basically equal to Rxx of 0. That is the value of the autocorrelation that it takes at tau equal to 0, and at tau equal to 0 this takes a value of 2, and therefore this P average is equal to 2, and this comes from figure. Okay, any questions? I'm taking these initial questions on WSS process just to make autocorrelation and other things, just to make you comfortable with this concept of autocorrelation PST, so that you can catch up the upcoming things in a better way, which will come up in upcoming lectures. Okay, if there are no questions, then let us go ahead with the fifth question that I have planned today. So it says that the autocorrelation function of a WSS process is e power minus 2 magnitude of tau or mod tau, and we need to find the peak value of its PST. Okay, so as mentioned earlier, let's say this. As mentioned earlier, this autocorrelation function and the PST are Fourier transform pair. So let's say this process is xt. So this phi xx of tau is basically e power minus 2 magnitude tau. So this phi xx of f will be basically Fourier transform of phi xx of tau. And we need to find the maximum value of this. Okay, so now let us look at this. So phi xx of f will be equal to integral minus infinity to infinity e power minus magnitude minus 2 magnitude tau e power minus j 2 pi fc tau d tau. Now this I can write as, I can split this integral into two parts, one from 0 to infinity and another from minus infinity to 0. So let's have it from minus infinity to 0. In minus infinity to 0, this magnitude of tau is basically equal to minus tau. So this comes out to be e power 2 tau into e power minus j 2 pi fc tau d tau plus integral 0 to infinity, and this comes out to be e power minus 2 tau into e power minus j 2 pi fc tau d tau. This I can write as minus infinity to 0 e power 2 1 minus j pi fc tau d tau plus integral 0 to infinity e power minus 2 1 plus j pi f. Why am I having fc here? There's no fc, it's just f. It's not a carrier. Extremely sorry, this is just f tau d tau. Okay, so what are we having? So we are having this equation. Let me just copy paste it on next page. Yeah, this is what we are having. This is phi xx of f. So the first integral will be e power 2 1 plus 1 minus j pi f tau 2 1 minus j pi f, and this has to be evaluated from minus infinity to 0, plus the second integral gives e power minus j 1 plus j pi f tau whole divided by minus 2 1 plus j pi f, and this has to be evaluated from 0 to infinity. So this is equal to 1 upon 2 into 1 minus j pi f minus e power 2 1 minus j pi f into minus infinity, and e power minus infinity will go to 0. So the second term is basically 0 plus the first term here is e power minus infinity, so that will again go to 0, and the second term will give me 1 upon 2 times 1 plus j pi f. Now if we take the LCM of the denominator, what we have is 1 plus j pi f plus 1 minus j pi f upon 2 into 1 plus pi square f square. This gets cancelled, so we have 2 upon 2 into 1 plus pi square f square, which comes out to be 1 upon 1 plus pi square f square. Now if you observe carefully, this thing here, this thing decays with 1 by f square. That is, this thing, this PSD equation that we have obtained will be looking something like this. At f equal to 0, this will attain a value of 1. Let me write it properly. This will be my phi xx of f. This is f, and as we tend to infinity, this thing will go to infinity, something like this. Okay, which means that the maximum value or peak is attained at f equal to 0, which implies that phi xx of f max is given as phi xx of 0, which comes out to be equal to 1. Any questions at this point? So this is the final answer that we wanted. Any questions? Okay, if there are no questions, then let us go to the next question that I have planned today. So this is the 6th question that I have planned to cover today. What does it say? It says that if Sx of f is the power spectral density, so this Sx of f is PSD of a WSS process xt, and we need to find PSD of Sy of f of the process yt equal to x of 2t minus 1. Now, what do we know is, let's see, what we'll do is, let's see, or let Rx of tau be the autocorrelation function of xt, and Ry of tau be the autocorrelation function of yt. So what does this mean? This Rx of tau is basically expectation of x conjugate tau, x of t plus tau, and this Ry of tau will be equal to expectation y conjugate of tau into y of t plus tau, and we need to find Sy of f, which is PSD of this yt process. So this will be basically Fourier transform of Ry of tau. This is we need to find. Okay, so in order to find this Sy of f, what we need to find first is this Ry of f. Another thing to note here is this Sx of f is equal to Fourier transform of Rx of tau, and this is given. So using this given information, we need to find this Sy of f. So first we need to find this Ry of f, and then we need to find the Fourier transform of this Ry of f. Another thing to note here is we have been only given the relation between this yt and xt process. So now using or exploiting this relation that we know, we'll try to find out Ry of t in terms of this Ry of tau in terms of or as a function or in some form related to this Rx of tau. So what we have been given is this y of t is simply x of 2t minus 1. Therefore, Ry of tau is equal to expectation y of t. I made a mistake here. Y conjugate of t into y of t plus tau. Okay, this is the autocorrelation function. So this we can write as expectation of x conjugate of 2t minus 1 into x of 2c. This t here now has to be replaced by 2t minus 1 for x. So, or rather, in other words, this t here has to be replaced by t plus tau. So what do we have here is 2 times t plus tau minus 1. This comes out to be expectation of x conjugate 2t minus 1 into x of 2t plus 2 tau minus 1. I'll just rearrange the second term. So this is equal to expectation x conjugate of 2t minus 1 to x of 2t minus 1 plus 2 tau. Okay, so now what we'll do is let 2t minus 1 equal to t1. So this Ry of tau comes out to be expectation x conjugate t1 into x conjugate 2t t1 plus 2 tau. Now just look at this equation that we have written here. This Rx of tau is basically expectation of x conjugate of t multiplied by x of t plus tau. So if I consider this equation here, so this thing that is coming here, this Rx of tau is basically depending only on the difference of these two time instants. That is t plus tau minus t, which comes out to be this tau. So basically this autocorrelation depends only on the difference between the two time instants. Now instead of tau, here we are having 2 tau. So if we compare with this equation here and this equation, what this comes out as, this is nothing but Rx of 2 tau. So Ry of tau is basically Rx of 2 tau. So this is the relation between my y of the autocorrelation function for the process xt and the process yt, which are related in this fashion. Okay, and now what we need to do is Sy of f will be equal to Fourier transform of Ry of tau, which is equivalent to finding the Fourier transform of Rx of 2 tau. Okay. So let us do that explicitly. We can make use of the properties of Fourier transform. However, I'll right now do this from scratch, but we'll get to some property of Fourier transform just to revise, or in case we forget the property of Fourier transform, how to go ahead from this step. It will be much more clear. So what we are having here is Sy of f is equal to Fourier transform of Rx of 2 tau, which is nothing but integral minus infinity to infinity Rx of 2 tau into e power minus j 2 pi f tau d tau. Now what we'll do here, let 2 tau equal to some tau 1, which means that tau equal to tau 1 by 2, which means that d tau is equal to d tau 1 by 2. Therefore, Sy of f comes out to be integral minus infinity to infinity Rx of tau 1 e power minus j 2 pi f tau 1 by 2 into t tau 1 by 2. So this I can write as 1 by 2 integral minus infinity to infinity Rx of tau 1 into e power minus j 2 pi. I'll write this as f by 2 tau 1 t tau 1. So let me call this as equation 1. Now what we'll do is, we know that this Sx of f is basically Fourier transform of this Rx of tau. So we'll explicitly write the equation for Sx of f. So let's say this Sx of f, which is nothing but Fourier transform of Rx of tau. This is nothing but integral minus infinity to infinity Rx of tau into e power minus j 2 pi f tau d tau. This is equation 2, let's say. Now if we compare this integral here and this integral here, now if we compare these two integrals, it can be clearly seen that this integral is simply Sx of f, this integral, but now evaluated at f by 2. Instead of f, now it is evaluated at f by 2. So from equation 1 and equation 2, we have Sy of f is equal to 1 by 2 Sx of f by 2. So this is what we are having here. So this Sy of f is simply 1 by 2 Sx f by 2. So now instead of going through all of these, there is a property of Fourier transform which we can directly exploit. So I'll write that property explicitly so that it can be handy in solving maybe your exam question or any other questions. So property of Fourier transform. So if xt and xf are a Fourier transform pair, then xat and 1 by magnitude a x of f by a are Fourier transform pairs. So this is a property of Fourier transform that we would have just exploited. We were having Rx of 2t, so here a was 2. So if Rx of tau has Fourier transform as Sx of f, then Rx of 2 tau will have Fourier transform of 1 by magnitude of 2 into Sx of f by 2, which is equivalent to 1 by 2 Sx of f by 2, which we have obtained here. We would have reached to same way, to same answer. However, just in case we forget this property, it is easy, it is simple to go away with the standard or conventional method to solve, or using the first principles of Fourier transform and get to the desired answer. Any questions? Okay, if there are no questions, then I'll go to the next question that I had planned to cover today. So here what is given is the low pass equivalent of a PAM signal, that is pulse amplitude modulation signal, is ut equal to summation over n running from minus infinity to infinity in gt minus nt, where gt is a rectangular pulse, and let in, this in is given as en minus 1, and the sequence an takes a value from 1 minus 1. This sequence an is uncorrelated and it is equiprobable. Okay, so what all information do we have? This ut is the PAM signal that we are having, which is constructed using the information sequence, which is in, and this in is constructed using these ans, which take the value 1 and minus 1, and these two are uncorrelated. These two are uncorrelated and are equiprobable. Okay. I hope this is clear. Any questions? So now what we have been asked is we need to find the autocorrelation function of in, and we need to find, after that we need to find the PSD of this signal ut. So we'll start with finding the autocorrelation function of this in. So what we need to find is, we need to find phi I of tau, or instead of tau, let me say m, which is simply expectation in into in plus m. This is what we need to find. So now, if in order to find this, what we'll do is we'll substitute the value of in as en minus 1 and en plus m minus en plus m minus 1 . Okay, now this we can write as expectation of en plus m minus, or let me write it, minus en plus m minus 1 minus en minus 1 en plus m plus en minus 1 plus m. So now I can have the linearity of expectation. So this comes out to be en plus m minus expectation of en plus m minus 1 minus, or let me take it to the next page, it will be too much cluttered here. So let me add a page. So this phi I of m, this comes out to be expectation of en into en plus m minus expectation of en plus m minus 1 minus expectation of en minus 1 into an plus m plus expectation of en minus 1 an plus m minus 1. Okay, we need to find this. Now what we'll do is, let's say m equal to 0. So if m equal to 0, then phi I of 0 comes out to be expectation of an into an plus 0, which is an square minus expectation of en into an minus 1. Now this, okay, let me write it explicitly, an into an minus 1 minus expectation an minus 1 en plus expectation an minus 1 into an minus 1, that is an minus 1 square. Okay, now let's consider this expectation of ai square for all I ranging from minus infinity to infinity. So this comes out to be, now you observe this ai belongs to minus 1 and plus 1, and these two are equiprobable. So this comes out to be minus 1 square into 1 by 2 plus 1 square into 1 by 2. So this comes out to be 1. And if we consider ai, aj, and this is for I not equal to j, for all I not equal to j, this is equal to expectation of ai into expectation of aj. Why? This comes out because ai is uncorrelated sequence. This comes out from the definition of uncorrelated sequence. Okay, so and now let us consider this expectation of ai. So this comes out to be minus 1 into 1 by 2 plus 1 into 1 by 2 multiplied by minus 1 into 1 by 2 plus 1 into 1 by 2, and this comes out to be 0 into 0, which is equal to 0. So therefore, if I am getting a term which is of the form expectation of ai square, that will contribute to 1. Otherwise, if I am getting a term as expectation of ai into aj, then that will correspond to 0 when I is not equal to j. So if we have that case, then if we look at this term here, so let me just take this and copy to the next page. So this phi I of 0 is something like this. So if you observe carefully, this term here and this term here will be equal to 1. However, these two terms, n is not equal to n minus 1 in both of these cases. Anyway, n is never equal to n minus 1. So these two terms will be equal to 0. So what we are having here is 1 plus 1, which comes out to be 2. This is the first thing that we have obtained. Now let us take this, copy here. Yeah. Now let us consider the case where this m equal to 1. Or what we can do is, instead of going case wise, let us say that we have this phi aa of m equal to expectation of an into an plus m, and this comes out to be equal to 1 if m equal to 0, and it is 0 if n equal to m not equal to 0. So now what we can do is, we can write this as phi aa of m minus phi AA of difference between these two quantities, this and this. So this will be m minus 1 minus phi AA of this quantity, this quantity subtracted by uh, this quantity subtracted from this quantity, so that is n plus m minus n plus 1. So this comes out to be m plus 1 plus phi AA of the difference between these two quantities, which is basically equal to m. So instead of writing that, what I can do is I can just have a plus 2 here. I'm sorry, 2 times this. So now if we have here, so what we observe is, in order to have this term non-zero, either this term should be equal to 0, or this term should be equal to 0, or this term should be equal to 0. So what we observe here is, if my m equal to 0, then this term survives and these two go to 0, because this will be phi AA of 1 and phi AA of minus 1 and phi AA of 1. So these two will be 0 by this definition what we are having here. However, this will survive. So as observed from this previous discussion, for m equal to 0, this phi II of 0 will be equal to 2 times phi AA of 0 minus phi AA of minus 1 minus phi AA of 1, which comes out to be equal to 2. If I am having m is equal to 1, then this phi II of 1 is equal to 2 times phi AA of 1 minus phi AA of 0 minus phi AA of 2, and this comes out to be minus 1. Similarly, if I have m is equal to minus 1, then we have phi II of minus 1, which comes out to be phi AA of minus 1 minus phi AA of minus 2 minus phi AA of 0, and again this comes out to be minus 1. So this is what we are having. Now if we substitute m other than these three values, all of these quantities, that is this m minus 1 and this m plus 1, will be non-zero. For all other values this will be non-zero, and for all other values of m, this quantity will give me a value 0. So if we summarizing, what we have is, this phi I of m is equal to 2 if m equal to 0, it is minus 1. So this is minus 1 if m equal to plus minus 1, or let me write it individually. F equal to 1, it is minus 1. If m equal to minus 1, it is 0 otherwise. And this thing here is nothing but autocorrelation of IN, the sequence IN. Any questions? Okay, if there are no questions, then let us go with the next question, that next subpart of this same question. So what is given is, we need to find the PSD of this signal UT, where this UT is given by this formula here, and this GT is rectangular pulse. Now if we go back to our discussion of the content, yeah, so just look at this equation which is given here. We need to find this thing, we need to find this thing which is phi VV of f, which comes out to be 1 by t magnitude GF square phi I f. So this is what we need to find, and this phi I of f comes out to be this quantity. So let me write it explicitly for our sake of handiness. So what we are having is, yeah, we need to find phi u of f. Here we are having u, not v. So just to be consistent with our notations, so this comes out to be phi u of f, which is equal to 1 by t magnitude gf square phi I of f, where this phi I of f comes out to be summation m running from minus infinity to infinity. So this is simply Fourier series. Fourier series of this phi I of m minus j 2 pi f m t, sorry, fm capital T, and this g of f is equal to Fourier transform of gt. Now here this gt what we are having here is nothing but a rectangular pulse, and for rectangular pulse, let me write the equation. This gt is rectangular. Let's say it is of this form, e for 0 to t, and for this gf is equal to at sine pi ft upon pi ft into e power minus j pi ft. Okay, so if we have this information, this phi u of f is equal to 1 by t multiplied by magnitude of this quantity g of f, and this g of f, as mentioned here, is magnitude square of this. So we need to substitute this equation here. So what we have is, so we have it as at sine pi ft upon pi ft into e power minus j pi ft square phi I of f. This comes out to be 1 by t a square t square sine square pi ft. Let me write it properly. 1 by t at square sine pi ft upon pi ft square, and the magnitude of this e power minus j to j pi ft is simply 1, and this has to be multiplied by phi I of f, and let me number this as equation 1. So what we need to do is, we need to find phi I of f. So this phi I of f is simply Fourier series of this phi I of m, which is equal to summation m running from minus infinity to infinity phi I of m into e power minus j this is e power minus j 2 pi fm t. Let me just check if I have mentioned it correctly. Yeah, j minus j 2 pi fm t. Okay, now this phi I of m is obtained here. So let me just write it again. This phi I of m is equal to 2 if m equal to 0, and minus 1 if m equal to plus minus 1 and 0 otherwise. Okay, so if we have this situation, then this I can write as phi I of 0 into e power minus j 2 pi f 0 t, which is 1, plus phi I of 1, which is simply minus 1. So this is minus e power minus j 2 pi f t minus 1 into e power j 2 pi f. So this thing corresponds to 1 and this thing corresponds to minus 1. So this thing is pi I of 1, this thing is pi I of minus 1, to be very clear. So now this pi I of 0 is 2 minus, I can take outside, so this is e power j 2 pi ft plus e power minus j 2 pi ft. Let's multiply and divide by 2, something like this. Now this quantity here, this quantity is simply cos 2 pi ft. So this is 2 minus 2 cos 2 pi ft, which I can write as 2 times 1 minus cos 2 pi ft. And this 1 minus cos 2 pi ft is basically 2 times sine square pi f. So this is 4 times sine square pi f. Okay, so what we are having is this pi I of f is simply 4 times sine square pi ft. Therefore, from equation 1, that is from this equation, this phi uu of f is equal to 1 by t at square sine 2 pi, sine pi ft upon pi ft whole square multiplied by phi I of u, so that comes out to be multiplied by 4 times sine square pi f. So this is the final value for the PST of ut. So this thing is PST of ut. Any questions? Okay, if there are no questions, then let's go for the 8th question that I had planned to cover today. So what we need to do is we need to find g of f if gt is as shown in this figure. Okay, so this is the gt that we are having, and we know that this g of f is simply Fourier transform of gt. So let me write it explicitly. This g of f is simply Fourier transform of gt. So now what we can do is we can apply the definition of Fourier transform. So this comes out to be integral minus infinity to infinity gt into e power minus j 2 pi ft dt. Now if you observe carefully, this gt is non-zero only for a range of 0 to capital T. And if that is the situation, instead of integrating over a limit from minus infinity to infinity, I can just integrate it over a limit of 0 to capital T. Now another thing to note here is from 0 to t by 2, this gt takes a value of 2, and from t by 2 to t it takes a value of 1. So I can simply split this integral into two parts, which is equal to integral minus infinity to infinity gt, which is 2 e power minus j 2 pi ft dt. Oh, I'm sorry. I can split it in two integrals. One is from 0 to t by 2. Gt is 2 here into e power minus j 2 pi ft dt plus integral t by 2 to t, and for this range this is equal to 1 into e power minus j 2 pi ft So this is what we are having here. So what we'll do is we'll take up this integral first and try to simplify this. So I'll just do this as 2 times I1 plus I2, where this I1 is simply integral 0 to t by 2 e power minus j 2 pi ft dt. Okay, let me have this as equation 1. And this I2 is equal to integral t by 2 to capital T e power minus j 2 pi ft dt. Now let us do a change of variable. So what we'll do is, let's say this t1 is equal to t minus t by 2, capital T by 2, which means that this t is simply t1 plus capital T by 2 and dt is simply equal to dt1. If that is the case, then limits change from t1 equal to 0 to t by 2. Okay, so therefore this I2 now becomes integral 0 to t by 2 e power minus j 2 pi f t1 plus capital T by 2 dt1. Now this I can write as integral 0 to t by 2 e power minus j 2 pi f t1 dt1 multiplied by e power minus j 2 pi f capital T by 2. I can take this out. Because this is not a function of t1. So I can safely take it out. So this is simply this thing here. If we compare it with the equation 1, this is simply equal to I1. So this comes out to be I1 times e power minus j, this 2 and this 2 gets cancelled. So this is simply e power minus j pi f capital T. Okay, so what we have is this g of f is equal to this g of f is equal to 2 times I1 plus I2, which comes out to be 2 times I1 plus e power minus j pi ft I1, that is 2 plus e power minus j pi f capital T times I1. So let me have this as equation 2. And from equation 1, we have this I1 as integral from 0 to capital T by 2 we have this equation here. Make some mistake. No. Okay, this is fine. T by 2 e power minus j 2 pi ft dt. This is simply e power minus j 2 pi ft upon minus j 2 pi f from 0 to capital T by 2. This comes out to be 1 minus e power minus j 2 pi f capital T by 2 upon j 2 pi f. So this comes out to be 1 minus e power minus j pi f capital T upon j 2 pi f. So what we are having is this I1 is simply 1 minus e power minus j pi f capital T upon 2j pi f. You can take out minus j pi f capital T by 2 outside. So what we are having here is e power j 2 pi f, sorry, j pi f T by 2 minus e power minus j pi f capital T by 2 whole divided by, or let me do this, divided by pi f and this divided by 2j, and this quantity here is simply sine of pi f T by 2. So this comes out to be e power minus j pi f T by 2 upon pi f into sine of pi f T by 2. Okay, therefore g of f is simply this quantity. Let me take it there. Yeah, which is simply equal to 2 plus e power minus j pi f capital T multiplied by e power minus j pi f T by 2 into sine of pi f T by 2 upon pi f. Now, just for the sake of completeness, this is the equation that we were looking at. But what we'll do is, we'll write this as 2 plus cos pi f t minus j times sine pi f t into e power minus j pi f t by 2 into sine of pi f t by 2 upon pi f. Now let us look at magnitude of gf square. So this will be basically magnitude of this quantity, which is 2 plus cos pi f t minus j times sine pi f t square multiplied by magnitude square of this quantity. The magnitude square of this quantity is simply 1, and magnitude square of this quantity will be simply square of this quantity. So this will be into sine pi f t by 2 square, or let me do this way, on pi f whole square. So now this comes out to be 2 plus cos pi f capital T square plus sine square pi f capital T multiplied by sine of pi f T by 2 upon pi f whole square. Now this I can write as 4 plus 4 cos pi f t plus cos square pi f t plus sine square pi f t multiplied by sine of pi f t by 2 upon pi f whole square. Now this quantity, this is equal to 1. So this magnitude of gf square is simply 5 plus 4 cos pi f t multiplied by sine pi f t by 2 upon pi f square. And let me number this as equation I. Okay, so this is the equation for gf that we had to find, and additional thing that we found out was this magnitude gf square. Any questions? Okay, if there are no questions, then Then let us look at the next question that we need to find. So what is given is an information source generates in, a sequence in for this n ranging from minus infinity to infinity, and this is an uncorrelated sequence. So let me write it properly. This is independent. Okay, now this in has some probability distribution which is 2 0 minus 2. In takes three values which is 2 0 minus 2. It takes 2 with probability 1 by 2, 0 with probability 1 by 2, and minus 2 with probability 1 by 4. I'm sorry, 2 with probability 1 by 4, 0 with probability 1 by 2, and minus 2 with probability 1 by 4. Now the information bearing signal is given by this equation Vt is equal to minus infinity to infinity in gt minus n capital T, and we need to find the PSD of the signal Vt. And what do we need to do is we need to assume this gt as defined in this question 8. That is, this gt is given something like this. So therefore this gt will have a Fourier transform as this or this, and the magnitude of gf square is simply this. Okay, so what we need to find is to find phi vv of f, which is simply 1 by capital T magnitude of gf square into phi I of f, and this is nothing but 1 by T multiplied by this quantity. So let me write it down so that I have good amount of space. So this is simply 5 plus 4 cos phi ft multiplied by sine of phi f capital T by 2 upon phi f whole square multiplied by phi I of f. So basically we need phi I of f. So this is what we need to find now. So let me write it again. So find phi I of f, and we know that this phi I of f is nothing but summation m running from minus infinity to infinity phi I of n multiplied by e power minus j 2 pi f m capital T. So this is the first thing that we know. Okay. Okay. So this is what we know. Now this in is simply 2 with probability 1 by 4, 0 with probability 1 by 2, and minus 2 with probability 1 by 4. And this phi I of m is basically expectation of in into in plus m. Now these are we know that this sequence is uncorrelated, which means that this is equal to expectation of in square if m is equal to 0, and it is equal to expectation of in into expectation of in plus m if m not equal to 0. And this is coming from definition of uncorrelatedness. Okay, this we know. So basically what we need to find now, we need to find expectation of in square and expectation of in. Now another thing to be noted is this in is distributed in similar way for all the values of n, which means that expectation of in will be exactly equal to expectation of in plus 1. Those two instances, those two time instances are identically distributed, and therefore we just need to find what is expectation of in and what is expectation of in square. So now let us find expectation of in, and this comes out to be in takes three values. The first value is 2 and this value is taken with probability 1 by 4. Next value is 0 and this is taken with probability 1 by 2, plus the last value is minus 2 and this is taken with probability 1 by 2. 1 by 4. So what do we have is 1 by 2 plus 0 minus 1 by 2, which comes out to be 0, and to know, it should be noted that this is exactly equal to expectation of in plus m. Okay, now let's look at expectation in square. So this is equal to the first value square, that is 2 square, into its probability, that is 1 by 4, plus 0 into its probability 1 by 2, plus minus 2 square into its probability 1 by 4. So this is equal to 4 into 1 by 4 plus 0 plus 4 into 1 by 4, which is equal to 1 plus 1, which comes out to be equal to 2. And therefore this phi I of m is equal to 2. See, at for m equal to 0, this is only expectation of in square, which comes out to be equal to 2 if m is equal to 0, and when m is not equal to 0, this is equal to and when m is not equal to 0, this is equal to simply 0. Okay, so this is what we are having here. Fine. And therefore what we are having is this phi I of f this phi I of f comes out to be summation m running from minus infinity to infinity phi I of m into e power minus j 2 pi f m t fm capital T, which comes out to be 2 into e power 0 plus 0, which is simply 2. And therefore this phi I of f, this phi I of f comes out to be 2. So what we are having here is, after substituting this in this phi VV of f, let us take this equation back. So this is what we are having. Therefore phi VV of f is equal to this thing, so let me write it, 1 by t 5 plus 4 cos pi f t multiplied by sine pi f capital T by 2 upon pi f whole square multiplied by phi I of f and this comes out to be 1 by t into 5 plus 4 cos pi f t multiplied by sine pi f capital T by 2 upon pi f multiplied by phi I of f, which is simply, so I can just simply rearrange this to write it properly. So this pi v of f is nothing but 2 by capital T 5 plus 4 cos pi f t multiplied by sine pi f t by 2 upon pi f whole square. I forgot to write whole square. Yeah. So this is phi VV of f that we need to find out. So this phi VV of f is basically the PSD of this equation or this information sequence that we are, information bearing signal that we are transmitting. Any questions? Okay, if there are no questions, then let's go to the last question that I had planned to cover today. So what is given is this AN is 0, 1 IID, and I forgot to mention these are equiprobable. And equiprobable. So this is given, and Bn is An XOR with An minus 1. So this thing is XOR. And we need to find the PSD of this information signal Vt, which is equal to summation n equal to Bn Gt minus Nt. Okay, this is what we need to find. And again, what we'll assume is this Gt is from question 8. So this is what we'll assume. Okay, so we know that PSD of Vt is simply phi VV of f, which is 1 by t magnitude of Gf square multiplied by magnitude of Gf square multiplied by phi I of m. Okay, this is what we are having here. Now from equation I, we know that magnitude of Gf square is simply 1 by simply 5 plus 4 cos pi ft multiplied by sine pi ft by 2 upon pi f whole square. Therefore, this phi VV of f is 1 by t multiplied by 5 plus 4 cos pi f capital T multiplied by sine pi f t by 2 upon pi f whole square multiplied by pi I of f. This is not m, this is f, sorry. Yeah. Okay, this is what we are having here, and now we need to find phi I of f, or here let me be very precise. Here the information carrying signal is not I, it is B, so I'll just write it as phi BB of f. I'll also write it as phi BB of f. So what we need to do is we need to find phi BB of f, and this phi BB of f is simply summation m running from minus infinity to infinity phi BB of m into e power minus j 2 pi fm capital T. And therefore, in order to find this phi bb of m, we first need to find phi bb of m. Okay, and this phi bb of m is simply equal to expectation bn into bn plus m. Okay, so this we know. Fine. So now this we can write as expectation of okay. So yeah, this, let me just have an equation here like this. Fine. Now if we observe carefully, yeah, okay, let me substitute also. So this is equal to expectation of an XORed with an minus 1 multiplied by an plus m XORed with an plus m minus 1. If you observe carefully, this is not a general or simple equation, simple thing that we can have, right? Like XORing is not a simple linear operation, and we can't just simply multiply and have a stuff and apply linearity property and stuff like that. Oh no, we can't do it. But what we know is these these ANs, these ANs are IIT. However, this BN, this BN depends on previous also. So therefore, this is not IIT. These are not uncorrelated. These are not at all uncorrelated, and therefore we can't separate these out and have m equal to 0 case and m not equal to 0 cases. So this is not that straightforward. So in order to have this thing here, what we'll do is, instead of doing I mean instead of doing this, looking at this equation first, what we'll do is we'll first understand what are the statistics of this sequence En. Okay, so what we'll do is we'll first, let me have this as equation 1. Let us, I have actually converted to 1 previously, no, okay. Let us understand EM stats. Okay, so basically what we have is expectation of AM will be equal to 0 into 1 into its probability plus 1 into its probability, which is equal to 1 by 2. So this means that this is not a zero mean sequence. No, this is not at all a zero mean sequence. It is having a probability, it is having an expectation average value as 1 by 2. Now let us look at this expectation of AM, or let me write it as AN into AN plus M. Now this I can write it in two ways, that is expectation of AN square, where n not equal, where m not equal to 0, and write this as an into expectation of en plus m for m not equal to 0. First one is for m equal to 0 and next one is for m not equal to 0. So for this thing that we are having is 1 by 2 multiplied by 1 by 2, which comes out to be 1 by 4. So for m not equal to 0, this correlation comes out to be 1 by 4. However, when we look at this expectation of en square, so this expectation of en square will be basically 0 square multiplied by 0's probability, that is 1 by 2, plus 1 square into its probability, which is 1 by 2. So when it is an square, this term here, when m equal to 0, it is expectation of an square, and this comes out to be 1 by 2. So therefore, phi A of m It is equal to expectation of an into an plus m. This comes out to be 1 by 2. If m equal to 0, it is equal to 1 by 4 if m not equal to 0. This is what we are having right now. Yeah, so this is what we are having here. This is the first thing that we are having. Now let us look at this Bn is equal to an XORed with an minus 1. Okay, now this an belongs to 0 and 1, which means that this Bn will also belong to 0 and 1. Okay, so what does it simply mean is this Bn can take value 0 and 1 only. Okay, so now what we'll do is we'll take probability that Bn equal to 0 and yeah, probability that Bn equal to 0, and that comes out to be so this comes out to be probability. When will this XORing operation be equal to 0? When this an and an minus 1 both are same. That is, this will be equivalent to saying that this an equal to 0 and an minus 1 equal to 0 plus probability that an equal to 1 and an minus 1 equal to 1. So this is equivalent to saying that probability of an equal to 0 into probability of an minus 1 equal to 0. Why? Because an is an independent sequence. That's why we can productify these probabilities. Plus probability that an equal to 1 into probability that an minus 1 equal to 1, and probability that an takes 1 and 0, 1 or 0 is simply half because these two are equiprobable. Right, and that's why this comes out to be 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2, which comes out to be 1 by 2. Okay, now similarly, probability that the sequence Bn equal to 1 is simply equal to this is simply equal to probability that an equal to 0. So when will Bn, this XORing operation, be equal to 1? When an and Bn are not same. So that is equivalent to saying that probability that an equal to 0 and an minus 1 equal to 1 plus probability that an equal to 1 and an minus 1 equal to 0. Now this again I can write as probability that an equal to 0 multiplied by probability of an minus 1 equal to 1 plus probability that an equal to 1 multiplied by probability of an minus 1 equal to 0. Again these are equiprobable, so I can write this as 1 by 2 multiplied by 1 by 2 plus 1 by 2 multiplied by 1 by 2, which comes out to be 1 by 2. So this is what we are having right now. Okay. Now let us go back to this phi bb of m. And this phi bb of m was simply expectation of bn plus m. Now let's do one thing. What we'll do is let us look at the case where this m is equal to 0. So in that case, this phi bb of m is simply expectation of bn square, which is equal to 0 into probability that bn equal to 0 plus 1 into probability that bn square 1 square into probability that bn equal to 1. So this is 0 plus 1 into 1 by 2, which comes out to be 1 by 2. So this is the first thing that we have obtained here. Okay, so when m equal to 0, this phi bb of m takes a value as 1 by 2. Okay, now let us look at the cases when m is not equal to 0. Okay, so let's have this phi bb of m, and this is equal to expectation of an XOR. Let me write it properly. So this is bn into bn plus m. This I can write as expectation of an this is expectation of an XORed with an plus an minus 1 multiplied by an plus m XORed with an plus m minus 1. Okay, now under what circumstances will this bn be depend on bm plus n? So the question that we need to ask is, for what values of m not equal to 0, bn and bn plus m are dependent. So bm and bn plus 1 will be dependent. So bn and bn plus m will be dependent if at least two values, like at least. So how can we write it? This will be dependent for those values of m for which an plus m is equal to an or an minus 1 or an plus m minus 1 is equal to an or an minus 1. So if an plus m is equal to an, then m will be equal to 0. So that case we have considered. So this case is for m equal to 0, already done. So I can just remove this. So what we need to do is, for an plus m should be equal to an minus 1. So from here, this thing implies that for m equal to minus 1. Okay, for that situation, this will be a dependent quantity. Now let us look at this thing here. Now this an plus m minus 1 will be equal to an when this m is equal to 1. So this will be there when m equal to 1. This case we haven't looked at. Now this an plus m minus 1 will be equal to an minus 1 when m equal to 0. So this condition will come. This will be done when m equal to 0, and this is also already done. Okay, so what are the two possibilities of m for which these bn and bn plus m are dependent? So these are dependent only for m equal to 1 and minus 1. Therefore, for m equal to plus minus 1, bn and bn plus m are dependent. Okay, so now what we will do is, for all m which does not belong to 0, 1 and minus 1, Bn and Bn plus m are independent. Therefore, for these values, phi bb of m will be equal to expectation of Bn, Bn plus m, which will be equal to expectation of Bn into expectation of Bn plus m for all m which does not belong to 0, 1 and minus 1. We have just shown this. For all the values of m which are not in the set of 0, 1 and minus 1, these Bm sequence will be independent. This Bn and Bn plus 1 will be independent. Now we have found out this expectation of Bn earlier also. Like this quantity we have found out. This expectation of Bn we haven't found out. So this expectation of Bn, let me see this. No. Okay. So this expectation of Bn is simply 0 multiplied by probability, let me write explicitly, probability that Bn equal to 0 plus 1 into probability that Bn equal to 1. So this comes out to be 0 plus 1 into 1 by 2, which comes out to be 1 by 2. And therefore this phi bb of m is equal to 1 by 2 into 1 by 2, which is equal to 1 by 4, and this is for all m which does not belong to the set of 0, 1 and minus 1. Okay, now the only case that remains is when m is equal to plus minus 1. So now let us treat them individually. So let us look at the case 1 where m is equal to 1. So what do we have is this phi bb of m, or to be precise, this phi bb of 1 is simply expectation of En XORed with En minus 1 into En plus 1 XORed with En. Okay, so this is what we are having. Now, this is an XOR. This belongs to 0, 1. Similarly, this is another XOR. This also belongs to 0, 1. And therefore, this multiplication can again take values 0 and 1. So this can take values 0 and 1. And now, this entire thing, this multiplication that we are having, this shaded part is itself a random variable. Let's say some random variable c, let's say c1, some random variable c1 which can take value 0 and 1. Okay, so now if it takes, so this I can write as 0 into probability that c1 equal to 0 plus 1 into probability that c1 equal to 1. We change its color. Yeah. Okay, so this is simply equal to probability that c1 takes a value 1. Now when will c1 take value 1? It will take value 1 only when this quantity En XOR En minus 1 is equal to 1 and En plus 1 XOR En is equal to 1. So this I can write as, this is equivalent to writing probability En XOR En minus 1 is equal to 1 and En XOR En plus 1 is equal to 1. So now, if you observe carefully, the two quantities that are common, the only quantity that is common between these two is an. So what we'll do is, let's say, and this will be equal to 1 when an not equal to an minus 1, and this will be equal to 1 when an is not equal to an plus 1. So we'll have two cases again. Yeah, so we are having this. So what we can write it as, this an is equal to 1. Then in order to have this quantity equal to 1, what do we need to do is, we need to set this an minus 1 as 0. An minus 1 is equal to 0. And in order to set this quantity as 1, we need to set an plus 1 is equal to 0. And an plus 1 is equal to 0. Now suppose this an is equal to 0. Then in order to make this as 1, this an minus 1 should be equal to 0, should be equal to 1. So this an minus 1 should be equal to 1. Similarly, if we need to set this quantity as 1, we need to set this an plus 1 as 1. So this an plus 1 should be equal to 1. So what do we have here? So this is these are independent, so I can just productify. So this will be equal to 1 by 2 into 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2 into 1 by 2, which comes out to be 1 by 8 plus 1 by 8, which is equal to 1 by 4. Okay, so this is 5bb of 1. This is 5bb of 1. Now let us look at the last case, that is case 4. Let me write it properly. This is case 3. This is case 2. And this is case 1. Yeah. So now case 4, when m is equal to minus 1. So for m is equal to minus 1, we have 5bb of minus 1, and this comes out to be equal to expectation of an XORed with an minus 1 multiplied by an minus 1 XORed with an minus 2. Now again, this I can write as, again with the same logic which we had applied for m equal to 1, this quantity can take values 0 and 1. And this is a random variable which can take value 0 and 1. So this is equivalent, and this is equivalent to writing that this random variable takes value 0, that is 0 into its probability plus 1 into its probability. Now anything multiplied by 0 is 0, so this reduces to 1 into probability that this quantity is equal to 1. So I can write it as 1 into probability that an XOR an minus 1 multiplied by an minus 1 XORed with an minus 2, this quantity is equal to 1. And this I can write as, and this quantity will be equal to 1 only when the individual multiplication goes to 1. So this comes out to be equal to an XORed an minus 1 equal to 1, an XOR an minus 1 XOR an minus 2 is equal to 1. Now again, now if we look at this carefully, the common quantity in these two is an minus 1. So let us set this an minus 1 as 0. Now in order to have this quantity as 1, I need to set an is equal to 1. So n is equal to 1. In order to have this thing as 0, I need to set, this thing as 1, I need to set an minus 2 as 1. So an minus 2 is equal to 1 plus probability that an minus 1, now let us set it to 1. So in order to have this as 1, I need to set this an as 0, and in order to set this as 1, I need to set this an minus 2 as 0. So an minus 2 as 0. So this comes out to be 1 by 2 multiplied by 1 by 2 into 1 by 2 plus 1 by 2 multiplied by 1 by 2 multiplied by 1 by 2, which is 1 by 8 plus 1 by 8, which comes out to be 1 by 4. Again, we can productify this just because this AN is an IID sequence. It is an independent sequence. So this is coming out just because of the independent nature of this sequence. So now what we'll do is, so let us summarize. What we have found out is this phi BB of M is equal to 1 by 2 if M is equal to 0. This is equal to 1 by 4 if M equal to 1. 1 by 4 if M equal to minus 1. These are these two cases. This is for M equal to minus 1. This is for M equal to 1. And for M not equal to 0, 1 and minus 1, it is equal to 1 by 4. So this is equal to 1 by 4 if, otherwise. So I can write it as phi BB of M is equal to 1 by 2 if M equal to 0, and it is equal to 1 by 4 if M not equal to 0. So this is what we are having here, and now what we need to do is we need to find phi BB of F, which is simply summation M running from minus infinity to infinity phi BB of M into e power minus j 2 pi f m t. So this I can write as phi BB of 0 plus summation M running from 1 to infinity phi BB of M into e power minus j 2 pi f m t plus phi BB of minus M into e power j 2 pi f m t. Okay. So this phi BB of 0 is 1 by 2 plus summation M running from 1 to infinity. This phi BB of M for M running from 1 to infinity is 1 by 4, and even this is for phi BB for minus 1 to minus infinity. So this is same. So this I can write as e power minus j 2 pi f m t plus e power j 2 pi f m capital T. I can just do multiply and divide by 2. So what I have is 1 by 2 plus 1 by 2 summation M running from 1 to infinity, and this quantity here is simply cos of 2 pi f m t, and this thing here is phi BB of f. Now what we had to find was not this phi BB of f, but rather we wanted to find this quantity, that is phi BB of f, which is something like this. So I can just take this and paste it here. So this is what we wanted to find out. So therefore this phi BB of f comes out to be 1 by t 5 plus 4 cos pi ft multiplied by sine pi f capital T by 2 upon pi f whole square multiplied by this phi BB of f, which comes out to be 1 by 2 1 plus summation M equal to 1 to infinity cos of 2 pi fm. I can also write this one as cos of 2 pi f into 0 into t. So I can rewrite this equation as phi BV of f as 1 by t, I am taking this 2 and this 1 by this 1 by 2 and this 1 by 2 together, multiplied by 5 plus 4 cos pi ft multiplied by sine pi f capital T by 2 upon pi f whole square multiplied by summation m running from 1 to infinity cos m running from 0 to infinity cos of 2 pi fm capital T. So this is the value of the PSD of that information pairing signal, which was Vt. Okay, this is the final answer that we wanted to find out. This is the 5 eV of t, which is the PSD. Any questions at this point? This was all I wanted to cover today. If there are no questions, then you are free to leave the meeting. Thank you for attending today's session. Hope to see you all in the coming sessions. Thank you all.